Hello viewers, I'm Maryanne Martinez and we are here today with Stephanie Kwolek, the chemist from DuPont that created Kevlar. We're here to find out about herself, about Kevlar's creation, what it actually is, and finally how Kevlar is used today in the modern world. Thank you again, Ms. Kwolek, for taking the time to be with us here today. Why don't you start by telling us about yourself?
Well, dear, I was born 87 years ago in 1923 in New Kensington, Pennsylvania. My father died when I was about 10, but he's the one who interested me in the sciences. I first wanted to become a fashion designer, which I attribute to my mother, but then I decided that I wanted to become a doctor. But I could not afford to go straight to medical school since my mom was barely able to make ends meet. So I decided to get a degree that would land me in a temporary job that would both help me pay for medical school and help me in the medical field. I then went to Margaret Morrison Carnegie College to earn my bachelor's in chemistry.
It's funny how things work out that way.
Yes, it is, dear. It ended up being a perfect road for me.
Did you land a job after you earned your chemistry degree?
It certainly did, my dear. I was offered a job at DuPont's company's Textile Fabrics Laboratory in Buffalo, New York. I was then transferred to DuPont's Pioneering Research Laboratory in Wilmington, Delaware, where I became fascinated with the work so much that I decided to stay rather than going to medical school as originally planned. There, I worked as a chemical research scientist and practiced polymer condensation, which is the creation of long chains of molecules at very low temperatures.
Now, why don't you tell us about some of your achievements?
Well, let's see. During my career, I obtained 28 patents, but I am most known for creating Kevlar. I have won many awards in my time. A significant one was being the fourth woman to enter National Inventors Hall of Fame in 1996, and also entering the National Women's Hall of Fame in 2003.
That is amazing. You have sure come a long way.
Thank you.
What have you been doing since retiring from DuPont in 1986?
I still remain as a consultant for DuPont. I also serve the National Research Council and the National Academy of Sciences. I also give lectures on my career and inventions in chemistry, but also my current hobbies are sewing and gardening.
Thank you, Ms. Kwolek, for sharing some of this information about yourself. Now why don't we get down to it and talk about Kevlar?
Certainly, dear.
Can you tell us about when and how it was developed?
It happened while I was working in the Textile Fibers department at DuPont in 1964, I believe. This department was involved with developing industrial fibers. The project that this was trying to develop a new fiber that would be so strong and light enough to reinforce car tires so that it would waste less gas. This involved creating polymers, melting them into liquid, and then using a spinneret to spin them into fibers.
Do you mind briefly telling the viewers back home what a polymer is?
Not at all. A polymer is defined as a large molecule formed by the repetitive bonding together of many smaller molecules. The polymer Kevlar that I created was much different from the polymers we were used to working with in the lab. I had to try many different methods in order to get the polymer to melt. And when I finally did, it did not look like your typical polymer solution. Normally, the melted polymer would have sort of a thick consistency and was transparent. The consistency of the polymer was like water and had a cloudy substance. I then proceeded to filter the solution, but it still remained cloudy. After the process of melting the polymer, the next step is to send it to the spinneret to be spun into fibers. I then had to do some convincing of the operator of the spinneret to allow me my polymer to be spun because he thought the cloudy solution would clog his machine.
What happened then?
Well, it did not end up clogging his machine, that's for sure. It had spun out a fiber that I then sent out to be tested for strength and stiffness.
And what were the results of that test?
I had several tests done on the fibers to make sure that the results were consistent, because the first test had said that the stiffness was at least 9 times greater than anything I had made before. And thank goodness that all the tests were consistent, proving that it was a fiber with great potential.
So, what exactly is Kevlar, and what makes it so unique?
Well, honey, let me tell you. Kevlar is a polymer that has a crystalline structure. This crystalline structure was new to us in the fibers that came from polymers, which is why the solution was cloudy after melting instead of translucent. This was also significant because polymers with crystalline structures was something that had only been explored in theory by few.
Can you show us the structure of Kevlar?
Well, let me start by showing you a 4-benzene dicarboxylic acid and 4-diaminobenzene. Kevlar is made reacting these two with heat. This one and this one. Here you can see the structure of Kevlar after the heat is added. Right here. The rings that you see here are aromatic rings, and so it is classified as a polymeride. You can also see that elements involved are hydrogen, oxygen, and nitrogen.
Thank you. Now let's move on to what the creation of Kevlar led to in the future.
Well, as I said before, the goal of this project was at DuPont to come up with a lighter, stronger fiber to reinforce tires. Kevlar was the perfect fiber for this, but after presenting this to tire companies, they did not want to switch factories and machines to utilize it because of cost. The nerve.
I know.
Nevertheless, we knew this strong yet light fiber had great potential, so we designed a team to find uses for it. They found over 200 applications for it.